Hi, I'm Alberto Bonanno, and I am a researcher of the Italian Institute of Technology. In this presentation, I will talk to you about the Micro-4-Nano project that deals with nanotechnology merged with microelectronics. In this presentation, I will give you, at the beginning, an overview about nanosensor and the general Micro-4-Nano approach. And then I will focus on the three main topics, so the integration of nanomaterials on microelectronics, the design of low-power readout circuit, and how to organize the readout circuits and nanomaterials in high-density array on chip. Let's talk about the nanosensor and in particular on nanomaterials. Nanomaterials has at least one dimension in the range of nanometers or hundreds of nanometers, like carbon nanotube or semiconductor nanowires. The nanowires can be longer than 100 nanometers, can achieve micrometers range, but we can also talk about nanomaterials in case all the three dimensions are in the nanometer scale, as for nanoparticles. We can use nanomaterials for sensing because some nanomaterials show interesting properties for sensing. For example, high sensitivity to common quantity like UV light or visible light or temperature variation, pressure variation, but they can also functionalized to detect target object at nanoscale, like for biosensing. For example, to detect protein or other biomolecules, or to detect also specific gases. But some materials at nanoscales show properties, electrical properties, that can be really different from the electrical property at macro scale, as in the example, the graphene. All these materials that can show interesting properties for sensing, hereafter I will refer to nanosensor. And in particular to passive nanosensors, so only resistive and capacitive nanosensor. So when nanomaterials detect the target object, its sensitivity corresponds to a variation of the electrical properties, so resistance or capacitance. And if we consider the total resistance and capacitance of nanomaterials, we can distinguish three main contributions. The first one is a base contribution that depends mainly on the synthesis process of this nanomaterial or on the nature of this nanomaterial. So if it is conductive nanomaterials like carbon nanotube, or is a semiconductor nanomaterial like zinc oxide nanowires. But their resistance change also depending on a slow variation of the environment that can be also temperature variation or some changement in the parasitics of the environment. And then the third contribution is the real contribution due to the sensing property. If we consider to interface passive nanosensor, we need an electronic interface able to stimulate the nanosensor and read out the signal. So if we want to interface all kind of nanosensor, we need something like an instrument, so a high accuracy and multi-purpose, but this is not a solution that can be integrated in a final device for some application like biosensing. So we need to conceive something smaller, but we can move towards a solution on PCB, on board. But this solution, often it is not low power and small size. So the best solution to have a final device is a readout circuit designed on CMOS technology. So you can design your circuit as a low power, low noise, and small size that occupies a small area on silicon. But you have to select a subset of all the nanomaterials. For example, semiconductor nanomaterials. And in this presentation, the readout circuit that I designed will refer to semiconductor nanomaterials. The output of this electronic interface should be an analog or a digital signal compliant with commercial electronics to be integrated in the final device. When we are designing an electronic interface for nanomaterials, in particular for semiconductor nanomaterials, and where we have a signal in the order of picoampere, nanoampere, we have to take care about the noise sources. In particular, we can identify the coupling noise as the main noise sources at the interface between the nanosensor and the analog front end. And then in the circuits, the characteristic noise are the flicker noise and the thermal noise. But we have to add also quantization noise if we want to convert the analog signal to digital domain, to be processed and then to have the final characteristics depending on the sensed quantities. So the noises can affect the sensitivity of your system. The goal of the micro-4 approach is to reduce at maximum the coupling noise, integrating the nanosensor as close as possible to the readout circuit. One solution is to integrate the nanomaterials directly on the top of the silicon chip. In this way, you can conceive a sort of 3D IC where the first layer is a nano layer, and then you have different layers with different tasks, like readout circuit, another layer for processing data, to storage data, and then the transmission wireless. In this presentation, I will show you the implementation of an array of readout circuit where the nanomaterials are integrated on the surface of the silicon chip. And there is a one-to-one correspondence between the nanosensor and one replica of the readout circuit, so that the noise at the interface is reduced at maximum. And then the output of this readout circuit has to be compliant with a low power wireless transmission like the impulse radio ultra-wideband. But this design shows some challenging design aspect, For example, an high-density array can have some problems of high power density. So your circuit has to be low power to reduce this issue. But also, as to your design, your microelectronics design has to occupy a low area on silicon. In this way, you can increase the integration factor of your nanosensor in the same chip. And then, since your nanomaterial is not always the same, does not show the same characteristics, so it depends on the synthesis process, it depends also on the integration process on CMOS surface. So you have to cover a wide dynamic range for resistance and capacitance to be able to convert the electrical characteristic of your nanosensor. Now I will focus on the first step, so the integration of nanomaterials on microelectronics. There are three main approaches in literature. One approach is stochastic, so you have an integration area, usually an interdigitated metal electrode, and then you drop your nanomaterials on that area, and there is the probability of connection that is directly linked to the amount of nanomaterials you drop on that area and on the area of your metal electrodes. So to increase that probability, you have to increase the number of nanomaterials or the area of your interdigitated electrodes. The second solution is to grow the nanomaterials directly in situ, so on the electrodes where you want to integrate your nanomaterials. You place some seeds and then under some accurate chemical process you let your nanomaterial grow directly in contact on your metal electrodes. But this approach implies some chemical process at fixed temperature that are not always compliant with the CMOS process. So in this case you have a limitation in the nanosensor type that you can integrate on your microelectronics. The widely diffused approach to integrate nanomaterial with metal electrodes is the dielectrophoresis technique that exploits non-uniform electric field to attract the nanomaterials suspended in a solvent, so they are dispersed in solution. You can attract this nanomaterial using this electric field. The electric field induces some dipole on your nanowires and generates some torsional and attractive force to the nanomaterials. This force it can be attractive or repulsive depending on the K factor, so the Clausius-Mossotti factor. This factor depends on the permittivity of the solvent of the solution and the permittivity of the nanosensor, of the nanomaterial, and the permittivity is depending on the conducibility of the nanomaterial or on the solvent, and also the frequency of your electric field. This solution has already been used in literature. In this work performed by many universities in like MIT, Stanford. This work in literature assemble some nanomaterials on the top of silicon chip. But the amplitude of the DEP signal, the dielectrophoresis signal, can reach also 45 volt peak to peak. So it is too high for modern technology, and also this this approach implies that you have to create post-assembly metallization. So after that the integration process has been accomplished, you create by lithography this metallization and you connect the electrodes to the readout circuit. But this approach is high cost because you have to perform some lithography after the integration process. Recently, there are other attempts to integrate nanomaterials, in this case carbon nanotube, with CMOS technology. In this case, an array of 60 nanosensor has been created, and only one simple circuit has been placed to measure the electrical characteristics of the nanomaterials. But in this case, one single ROC manages all the array, all the whole array, but you don't have a device that is really real time, and also the readout circuit is affected by the noise of the multiplexer network conceived to manage to switch the input of the readout circuit from one nanosensor to the other one. If we assemble some conductive nanomaterials, probably we don't have a big issue. But if we have to measure a signal from nanosensor that is in the order of nanoampere, so if we use semiconductor nanomaterials, this approach is not suitable. So the idea is to create a chip where there is a correspondence one-to-one from the nanomaterials, the nanosensor, and the readout circuit. In this case, we receive from the fab, from the semiconductor fab, the silicon chip with a passivation layer on the top. We need to remove that passivation layer because we want to assemble the nanomaterial on the aluminum top electrodes that are covered by this passivation layer. So using the reactive ion etching or wet etching, we can remove this passivation layer. We have to protect the bond wire using some resin, and then we can drop a solution of zinc oxide nanowires and some solvent like isopropanol, for example, isopropyl alcohol, and then we have to apply an external signal for dielectrophoresis. For example, using a signal generator that is able to generate a triangle wave signal of 3 volt peak to peak with a frequency of about 1 megahertz. Then some nanowires are connected to the electrodes, Other nanowires are not connected, but are on the silicon surface, so it is not a big issue for the final application. And then you can measure the nanomaterials with the rock just below the nanosensor. If we want to reuse the same chip to integrate another kind of nanosensor, we can clean the surface using an acid attack and then reuse the same micro 4 nano chip. So in this way we create a sort of a CMOS platform for nanomaterial integration. In this presentation, I included a brief video regarding the dielectrophoresis on CMOS circuits. You can see that the nanowires are a single nanowire is approaching to the couple of electrodes where the electrical field is applied, the dielectrophoresis signal is applied, but a large part of nanomaterials are moving towards the right edge of the silicon chip. This is due to an external application of the DEP signal through the pads, so the large part of the electrical fields is concentrated on the pad area, because pads are larger than the microelectrodes placed on the top of the chip. So if we conceive an optimization of this process, we have to exclude external DEP sources. Moreover, if we want to assemble different nanosensors on the same chip, so if we want to apply different DEP signal on different microelectrodes, couple of microelectrodes, so we need independent input-output for the DEP, and so we have to reserve some I/O, some pads of our chip only for DEP process. For that reason, I conceived an integrated system, a sort of system on chip, where each couple of electrodes is connected to a DEP generator integrated on chip and a readout circuit. All these small system on chip is controlled with digital signals, so you can use an external microcontroller to manage the two phases, so the dielectrophoresis phase and the readout phase. The micro 4 nano process, the micro 4 nano fabrication process is always the same. But inside each element of the array, there is a DEP generator and a readout circuit. You must decouple the electrodes from the DEP circuit during the readout phase, and vice versa. You have to decouple the readout circuit from the DEP circuit during the DEP phase. This is due because the DEP circuit works at 3.3 volt and the readout circuit works at 1.2 volt. This is a sample schematic of the DP generator. So the output signal is a triangle wave signal. The frequency can be controlled and can be adjusted in the range 50 kilohertz to 1 megahertz. The voltage is about 3 volt peak to peak, and the bias, the current of the op-amp is used to adjust the frequency of the oscillating signal. The area of this DP generator is really small because it is only 0.005 millimeters square. This is a picture of the final prototype. So 8 elements in the array. Each element is composed by a single DP circuit that is associated to 3 couple of microelectrodes, and 1 readout circuit per couple of electrodes, so per nanosensor. The distance of the gap between the microelectrodes is different to catch different size of nanomaterials, but also to investigate properties of nanomaterials with different length. The area of this element, so a single DP circuit and a single readout circuit, is about 0.008 millimeter square, so more than 100 nanosensor per millimeter square. This is a picture of the nanowires assembled on the 3 couple of microelectrodes. And then I will talk you about the design of a readout circuit, low power readout circuit, for being integrated in a high density array. As I told, we want to interface semiconductor nanowires, so the characteristic resistance can be included in the range kilo-ohm, giga-ohm. Then we want a measurement system with a maximum error of about 1% and with a signal-to-noise ratio at least of 40 dB. If we can apply an AC signal, we can also measure the capacitance of the nanomaterials, and we can explore a new feature of the nanosensor. As I told, we have to design a low power architecture, but also small size. In literature, there are existing circuits for ultra low current interface. So, for example, this amplifier, ultra low current amplifier, is used to measure the current of the DC current of the nanomaterial, but it occupies more or less 0.34 millimeter square, and it consumes about 45 milliwatts. That is too much to be integrated in a micro 4 nano chip. On the contrary, compared to a traditional approach, so you measure a current and you amplify that current and you convert the current in voltage signal, this readout circuit is based on the conversion of the current, the nanosensor current, into the time domain. So designing a quasi-digital converter. Unfortunately, this circuit occupies more or less 0.42 millimeter square, and it consumes 15 milliwatts of power. But it can cover a large range of resistance from 1 kilo ohm to 1 giga ohm. So it is suitable for a semiconductor nanowire. We can distinguish two main approaches. One is the traditional approach, so convert nanosensor currents into voltage and then convert it to a digital value on n bit. But there is also an alternative approach that implies the design of quasi-digital converters. So the nanosensor current is converted to the time domain. So the output quasi-digital signal represents the analog quantity in the time domain. So a square wave with a variable frequency or variable duty cycle. And then you need only a time-to-digital converter that you can integrate in the final device using commercial electronics to convert that signal to the traditional n-bit representation. This approach is low power because it can be conceived using low complexity architecture, mainly based on oscillators. So the value of resistance and capacitance are converted to a specific frequency value and then converted to using an high frequency time to digital converter to n-bit representation. It is important to notice that the least significant bit in this approach is related to the standard deviation of to the jitter of your oscillation, and so the standard deviation associated to the measure of the mean value of your oscillation period. This is just the first readout circuit that has been designed. Is only a proof of concept based on a relaxation oscillator. The conversion curve is linear. This transistor, MN2 transistor, is placed to exploit the stacking effect and to reduce the leakage in your circuit when you measure high resistance in the range of giga ohm. And the performance of the circuit show that this approach can be improved, can be used for nanosensor interface. In particular, a low power design can be achieved, only about 9 microwatt of power consumption. And also the area of the IC is really small, so about 0.002 millimeter square. The signal to noise ratio is more than the design constraints, the original design constraints, and so we can exploit the oscillators to conceive an electronic interface for a nanosensor. This is, for example, a basic architecture of a relaxation oscillator that use a single Schmitt trigger that is improved by the use of an operational amplifier in parallel of this Schmitt trigger to increase the oscillation frequency of your system. This is due because an high resistive nanosensor makes the circuit oscillating at low frequency, and so the circuit is affected by the flicker noise. Increasing the oscillation frequency, we can increase the signal-to-noise ratio of our measurement system. In fact, this is the characteristic of the operational Schmitt trigger converter. It is linear in two regions, region A and B, following two expressions with two different coefficients, KB and KA. And the final performance show that the signal-to-noise ratio is higher than 40 dB in the whole range, and it is higher than 60 dB in the low range for resistance lower than 10 megaohm. So if we consider that we have to scale down with technology, we probably have to move toward a solution that implies only standard logic, so logic gates in our design. For example, in these readout circuits, we have designed two ring oscillator composed by logic gates, and that are self-synchronized. So when the oscillating signal is 1, even the oscillation, the ring oscillator number 2 is enabled, and so the output of this circuit is a pulse train where the number of pulses are proportional to the value of the resistance of the nanomaterials, and represents a coarse estimation of the resistance. Since it is a discrete value, it is related to the standard AD conversion. But the time that interleaves between the first pulse of the first train and the first pulse of the following pulse train is a time value. So a representation in the time domain, so a quasi-digital signal, and represents a fine estimation of the resistance of the nanomaterial. So since this circuit is designed using logic gates only, it is easily scaled down with technology for modern CMOS technology. This is the characteristic curve of the quasi-digital converter. Depending on the oscillation frequency of the reference ring oscillator, you have a different conversion curve. So for timer 1 at low frequency, and then timer 2, timer 3, and timer 4, you have 4 different conversion curves. The equivalent number of bits are 8 in the whole range. The area of this design is about 0.005 millimeters square, and the power consumption is about 50 microwatts. So it is suitable for a high density array. But if we consider that we integrate the nanomaterials on the top of a circuit, and then if we consider that the characteristic curve of nanomaterials, of a semiconductor nanomaterials, can be also asymmetric, so we probably need to measure the sensitivity of the nanomaterials in one quadrant of the IV curve and not in the other quadrant. So we need a readout circuit that is able to measure the resistance variation of the nanomaterials only in one quadrant of the nanomaterial, in the IV curve of the nanomaterial. This circuit is able to apply an AC signal to stimulate the passive nanosensor and to change the polarity of the applied stimulation signal. If we consider that the nanomaterials is placed between electrodes A and B, the voltage VAB can be positive with some offset also, with some DC value, but it can be also negative, depending on the if the electrode B is grounded or the electrode A is grounded. So the output signal of this circuit is a square wave with a characteristic time value T0 and T1, so time at 0 of the signal and time at 1, that are proportional. The time at 0 is proportional to the capacitance of the nanomaterial, and the time at 1 is proportional to the resistance and capacitance of the nanomaterials. Using these two values, we can calculate and we can distinguish the resistance and the capacitance variation. And we can investigate also the sensitivity of that nanomaterial to two different phenomena. For example, nanowire, for example, can be sensitive to UV light with a variation of the resistance, and can be sensitive to temperature variation that corresponds to a variation of the capacitance of the nanomaterials. In this picture, I reported the the estimation error of the resistance in 3 decades, so from 1 megaohm to 1 gigaohm, per different capacitance value. So this picture shows that the measurement error is always low than 3%, but in most part of the resistive range is always below 1%. This is the experimental results regarding the measurement error. If capacitance is estimated, is fixed at 0 picofarad, the error increased because the parasitics are more relevant. If we place a parallel capacitance of about 47 picofarad, the estimation error is decreased with an average value of 0.79%. Actually, we can also estimate the capacitance of the nanomaterial with a maximum error in a range from 0 picofarad to 1 microfarad with a maximum estimation error of about 3%. In this picture, I show an experimental setup with an external nano gap device, nano gap based device, where it is integrated zinc oxide nanowire. This device is connected from external pad to the internal readout circuit, and the final results show that with a stimulation of a UV LED, we can measure a variation of time t0 and time t1 that correspond to a variation of the resistance of nano wire from 267 megohm to 158 megohm, and also the capacitance change. So these experiments show that we are able to measure the variation both of resistance and capacitance of the nanomaterial. And this circuit is really promising because the power estimation show that the circuit consumes only about 15 microwatts during the operation. In the standby mode, it consumes only 100 nanowatt, and it is able to measure both the resistance and capacitance of the nanowire, performing a measurement in the 2 quadrants of the IV curve of nanomaterial. The signal-to-noise ratio is always higher than 45 dB, so the measurement system is really low noise. This is only a comparison with the state of the art. So if we notice that the power is about 1 or 2 order of magnitude below the standard in literature, the area is really small, so it is the smallest circuit in literature, and the range is about 3 decades for resistance and about 6 decades for capacitance. In this table is reported an old value from 0 to 100 picofarad, but actually this system, the circuit can measure from 0 to 1 microfarad. The performance of the circuit regarding measurement accuracy are a little bit worse than the best circuit in literature. But considering the power consumption and the small area, this is the suitable solution for being integrated in a high-density array architecture. Let's talk now on the design of an array architecture that includes a large number of readout circuits and nanosensor. In particular, the prototype chip, the M4N prototype chip that has been designed, includes 8 elements in the array. Each element is composed by 3 readout circuits, 3 nanosensor, and 1 DP generator. There are 5 enable signals to enable the the circuits in the different 2 phases, the dielectrophoresis and the readout phases. And then there are some configuration registers to set the some option of configuration of the readout circuit. Since all the signals are digital, the microphone nano chip can be configured by external microcontroller. The output signal of each ROC is a 1-bit signal, and the frequency of the oscillation frequency of this signal is proportional to the resistance or the capacitance of the nanowire. In that case, we have 3 output signal per element in the array, and if we want to transmit all this data of nanosensors at the same time to an external microcontroller, we need 24 signal I/O that are so 24 paths that are reserved only for output signal. If we want to reduce the number of I/O reserved for that task, we need to apply a timing multiplexing acquisition, so acquire and transmit only the signal of the first element and then the signal of the second element, and so on. All these signals, since they are quasi-digital signals, so more or less square wave, can be easily transmitted, and they are really compliant with the impulse radio ultra-wideband technology. In fact, the transmitter generates a pulse at 3.3 or 4 gigahertz in correspondence of a rising edge of the quasi-digital signal. Actually, if we want to apply a time multiplexing, we cannot guarantee a real-time acquisition, and so the final application is not really performant. The idea is to take inspiration from the biology. So neurons works with a transmission of pulses from one neuron to the other one. And so in this case, we have a system that, a measurement system that generates a square wave. And the important is not the value or the sequence of the bits, but is the frequency of the events. And so we can consider an event as the pulses in a neuron network. And so we need an arbiter that decide which events occur in a single channel, and then transmit that information to an encoder that encode that associates one symbol to a single readout circuit. In this case, we have at the output, and at the output bus, a sequence of symbols. In this case, we can reduce it. We can strongly reduce the output pad reserved for output signal, And we implement a sort of address event representation that is widely used for neural networks. In that case, the symbol associated by the encoder is not strictly the position of the nanosensor, but can be also some parameters that you include in your that you associate to some nanosensor. In that representation of the sequence of symbol in the address event representation bus, we can have also two symbols that has to be transmitted at the same time, because two events occurs in two different channels at the same time. In that case, the system has to discard one symbol. But this is not a big issue, because the following units for a signal process can be identified that one symbol is discarded, because the variation of the oscillation period cannot be so fast to have a double of the oscillation period. So the signal processing can discard the value related to 2 times tk, and so it can identify that the real value is tk for the channel k. Moreover, you can also implement a programmable decimation in the arbiter, so that the channel where an high rate of events occur, you can decimate these events and transmit only 1 event per 10 events at the input, for example. And so you reduce the complexity of the transmission in the AER bus. This approach has been used in our center, in our research center, to design a pressure sensor globe, where in each finger there is a pressure sensor. The pressure sensor built with nanomaterial, and also a specific quasi-digital ROC that transmits the signal to a central unit, where an arbiter and an encoder is implemented, and then a wireless transmission of the signal has been implemented using impulse radio ultrawideband. So it is a technology that can be used for different kind of application. Okay, taking conclusion, in this presentation I show a fast and low-cost approach for integrating nanomaterials on CMOS based on dielectrophoresis, and an integrated solution for dielectrophoresis has been presented, and allow us to design a multi-sensor and high-density array on the single chip. And then 4 different readout circuits have been proposed from the proof of concept to the most elaborated, the most complicated readout circuits. All these readout circuits are low power and low complexity, exploit a low complexity architecture, because they have to be integrated in a high density array. And then a biologically inspired approach has been proposed to route the larger number of output signal in an high density array. For sure, this approach can be improved. For example, it can be designed, and we are working on that. We can be designed a DEP generator that detects if one nanowire is integrated in real time, so it can be the electrophoresis can be stopped, and no more than one nanowire are attracted in the microelectrodes area. The aluminum electrodes of the micro 4 nano chip can be also metallized using different metal like gold, for example, to improve the contact resistance between, to reduce for sure the contact resistance between the electrodes and the nanosensor. And finally, as already mentioned, configurable arbiter and encoder can improve the performance of an addressive interrepresentation bus for transmitting the signal from readout, a large number of readout circuits. Thank you for the attention. And if you are interested, you can contact me on my email alberto.bonanno@iit.it.